Hi and welcome everyone to this session called How Hackers Attack Your Smartphones and Tablets with Emil Kvarnhammar from Truesec.
Thank you, everyone. Really happy to be here. My name is Emil. I work for Truesec, which is a Swedish company. We're based in Stockholm. We also have a satellite office in Seattle. We do penetration tests, code reviews, and other types of security-related work for our customers. We're also, lately, we've moved into the smartphone and mobile OS area, which is really exciting. And we're working with, for instance, mobile device management and mobile security in general. So what I'm going to focus on today is I'd like to give you an introduction to some of the different mobile security threats that we are seeing, and both on Android and iOS, since I think those are the two most interesting platforms in terms of market share. I'm going to show you a demo on how an attack could actually work in real life, and in case you install a malicious application downloaded from, for instance, Android Market. I'm going to give a couple of other examples of vulnerabilities, especially in the iOS platform, since the demo is on Android. And I get a lot of questions about antivirus on mobile platforms. So I'm going to discuss a little bit about that, what an antivirus product can do and what it can't do. And as a last point, I'm going to give you some examples of what we are seeing. So these are actual examples from code reviews and security reviews of mobile applications, both for internal usage within an enterprise, but also applications released to customers in Apple's App Store, for instance. So to begin with, I'd like to explain the different kinds of attack vectors that are applicable for a mobile device. So if this is the evil guy in the middle with his nice black hat, was the nicest hat I could find. If he would like to attack you as a mobile user, he can see it from many different angles. One case could be uploading an evil application or malware in Android Market or App Store. Another one could be utilizing a client-side vulnerability, for instance, in PDF reading, where we have seen many different examples, especially on the iOS platform, but also on many different other platforms historically, also on the desktop side. Of course, physical access, if someone gets hold of your mobile device, if you drop it on the bus or it gets stolen, something like that. Man-in-the-middle attacks, where an attacker either just did for eavesdropping your communication between the device and the network, or even intercepting and affecting the actual I/O in the traffic. Another target is actually the backup and sync data, because that can also affect the behavior of an application that you have downloaded if the attacker modifies the backup data, for instance. But especially backup data is especially interesting in terms of getting hold of secret information. So those are the primary attack vectors that we're basing our work on. So one could ask, what's the purpose with different kinds of attacks? And there are many different purposes that are general for both PC platforms and mobile platforms. For instance, as I mentioned, getting hold of secret information, and that could both be like emails, calendars, contact information in case that is a secret too, but like passwords, certificates in case you use X509 certificates for client authentication, VPN passwords, email passwords, all sorts of passwords. And but also with laptops and smartphones and tablets especially, attackers can utilize the camera or the built-in microphone to just spy on the user. And I'm sure you're familiar with what botnets are, where an attacker can remotely control several devices or several clients at the same time and make them do a directed attack to a specific target. But also, of course, controlling one separate device to impersonate a single user. Specifically for the mobile platform, we have some other interesting purposes, like getting hold of SMS photos taken with a camera, and spying and listening to phone calls, for instance, but also location data. We have seen already that examples of where both the platform and some different applications that many users are using actually leaks location data and caches location data in the device. And of course, if we get hold of such a device, either physically or if we can control it remotely, then we can also get access to that location data and track the user's behavior or track the user's movements. And in the same way, remote controlling, sending SMS or placing phone calls at a premium rate. By the way, how many of you are developing on smartphone platforms? Yeah, most of you, I guess, since this is a smartphone track. So I'm sure many of you are familiar with this picture, but I'm showing it since I'm going to use that as a basis of explaining the attack that I do in the demo. So just to explain quickly, this is sort of a general picture of how the modern mobile OSs work today, and where we have one dedicated area for the system software and one or many different areas or partitions where we place user information. If we look at the Android platform specifically, we have one partition called system, which is mounted as read-only, and that's the system software, of course. And of course, it's only the root user that can do a remount of that partition to get read and write access. And then additionally, if you are platform developers, maybe from Sony Ericsson, then you know that there are technologies to do additional protection under that, to write protect flash memory and things like that. But this is a conceptual picture. And on the data side, there is that's the partition where you have read and write access, and that's where all the installed applications, the user settings, and things like that get stored. But of course, the data partition is a sandbox storage, so you don't have full access to the entire data partition just because you're an app. And I'm sure all you know, or most of you know, that it's a sandbox environment where you only have access to your resources, and you get your dedicated sandbox for that specific app. And the only way to communicate with the system software is, or at least should be, through the public API. So let's go over to the demo. I'm going to show on this device. This is an Android device running Android 2.3.3. So it's a fairly recent version of Android, and there are quite many devices out there today. I'm going to go into more details about that later in the presentation, but there are quite many devices that are vulnerable to this attack. So I'm going to switch over to the camera here. See if I can. So this is a Nexus 1, and what I'd like to illustrate here is a user who has recently bought or downloaded for free my really simple proof of concept application. It's called Cool Puzzle, and I placed a shortcut on the desktop here. And Cool Puzzle is a quite useless app if you start using it. It's just like, you know, a simple image puzzle where you can move the pieces around using touch. But so this is just to illustrate that this could be any game or any application that the user has installed. And if you notice now, the background in the application switched from blue to black. And that's just something that I built in. It's a convenient way for me to know that I've taken control over the device. So it's just something that, well, it's good for me to look at it that way. But so now I know for sure that my malware has been installed. So I can go out of the application. I could even uninstall the application right now. But let's move to how we see this from the attacker's point of view. So I'm going to start up. Let's see if I can focus my virtual machine here too. So yeah, you could see it for a second or two, listening for incoming clients. So what the server did now was opening up a server port, listening for connections for any devices that has this malware installed. And just for the purpose of this demo, I use this as interactively controlling the device. But this could as well be automated and sending the same commands to hundreds of thousands of devices. So I'm going to test something simple to start with. Vibrate to 2000. Maybe it's hard for you to hear, but yeah. So it's just sending a vibrate command to the device. And another example, screen, for instance. Yeah. And let me close that. Let's look at the Wi-Fi keys. All right. So the Wi-Fi keys, if you're not familiar with this, the WPA supplicant in Linux is storing the Wi-Fi keys in clear text in Android. It's stored in clear text, but that doesn't necessarily mean that any application can access it, because it's protected so that only root or the Wi-Fi user has access to it, since there is a separate user in Android for Wi-Fi. But of course, since this is running with quite nice privileges, I have access to that. So I'm going to input a different command called shell. Can everyone see? Yeah, it's hard for me to move my table, but so I'm going to input an IP address and a port for a shell. And let's see if we can. Maybe we could shrink that a little. Rip. Is that better? Like that. And maybe move it like this. So maybe this is not as user-friendly as a regular terminal, but you can at least see that I'm running as the root user. And that means that I have full access to, for instance, /data/data, which is normally not accessible for the shell user, for instance, that you use when you connect via ADB. And something that also could be a little bit scary is that I'm able to, let's exit from that shell. I'm also able to send text messages. And anyone who's volunteer who want to give up their mobile number? Uh-huh. 0761 669905. All right, so what should I write? Hello world. Boo. Oh, 0761. Like that. Hello short this time. Works? Yeah. So I think that, no, I have one more. So for instance, I could do, so let's imagine that the device is just laying on the table in a secret, super secret meeting. I don't know if you know any guys who've worked at FRA in Sweden, the Swedish defense, sort of. But when they're in a secret meeting, they always pull the battery of their device because they don't trust that the platform is safe enough. So I could do start recording meeting.3dp. Don't tell anyone about this. Stop recording. Get recording. And let's exit. Files. Whoops. Sorry about that. Whoop. Make sure that I use the right directory here. Meeting. Don't tell anyone about this. Yeah. So, yeah, I think the next step is to do a live capture of the screen to always have an updated view of the screen the whole time. But I guess you understand the concept behind this. And to explain in more detail what's happening behind the scenes. So let's go back to this platform picture. And I did install this cool puzzle from Android Market. And after that, cool puzzle utilized vulnerability that it's a privilege escalation. So I get root access, which means that I can do a remount of the system partition to have read-write access. Remember, initially it's read-only access, but I remount it to read-write access. And after that, we move a funny payload to the system software. And after that, this backdoor communicates over the internet. It's a reverse connection, so I don't have to be on the same network as the device to do this attack. I can be anywhere on the internet. And the device simply queries the server for what the backdoor software should perform in terms of operations. And the problem, well, it's good, both good and bad with this platform design, but The good thing about this is that it's very easy to do a factory reset, because everything you have to do is wipe the data and applications area, and everything is restored as the device was from factory, basically, except for some platform updates, maybe, and except for my backdoor. That's still going to be there after the factory reset. So that's, of course, a big problem. And also, if we do over-the-air updates, maybe you already know that over-the-air updates are generically performed with delta. It's calculating a delta based on what you already have on the device and what you will have after the upgrade, which means not even an upgrade would help to get rid of this malware, because the update would only perform delta updates, and the delta update wouldn't affect this component. So how many of you are Android developers? That's about almost the same amount as smartphone developers. Okay, and I guess the rest of you are iOS developers or Windows Phone? Yeah, some. Oh, interesting. So, if you're an Android developer, I'm sure you're familiar with permissions. And one could always argue that, well, I wouldn't install this kind of application if it's a puzzle and I see that it requires internet permission and sending SMS and recording audio and frame buffer, read frame buffer permission. But the problem is root can do everything. It doesn't even require this kind of permission. So all that this application requires is the permission to read logs, which would sound pretty harmless, right? And also, by the way, read frame buffer, that's not even possible from a regular application. That's just something that system software can perform from security point of view, for security purposes, of course. So the iOS guys might wonder, well, that's not going to work on iOS, right? But if you read the news this week, you might have seen that a guy called Charlie Miller, he presented basically the exact same attack, but on iOS. And what he did was publishing and getting an application approved by the Apple App Store. And he did that in September 2011. The application, what Apple didn't know, is that the application loads code dynamically from a server. And based on what he tells the server to do, of course. So during the review phase, of course, it didn't load any code dynamically from the server, because in that case, it wouldn't get approved. But he published the attack this week, and that caused Apple to shut his developer account down for at least a year now. It's really interesting. A famous hacker called Kevin Mitnick, maybe you heard of Kevin Mitnick, he responded via Twitter about this, and he said, maybe you should tell Apple that they are suspended for 1 year from now on from getting updates about security issues in their software. So I think that's a pretty good response. But Charlie Miller's point here is, without a real application approved and uploaded in the App Store, people would never believe me that Apple would approve this in the reviewing process. So yeah, he really did this just to make a point. A different kind of attack on affecting iOS devices is something called Lost iPhone, Lost Passwords, that was released by German researchers from Fraunhofer SIT. And what they do is performing a jailbreak over USB. And after the device is jailbreaked, you can extract keychain secrets from the device. And of course, that requires physical access. But remember, it's pretty easy that one of the users within your company, not you, of course, but anyone else within the company might lose their device or might get their device stolen. And the interesting thing here is that it doesn't even help if you have encryption, which you basically have in all the devices from 3DS and the first iPad, for instance. But that doesn't help, and passcode doesn't help either, because there are quite many secrets that are stored in the keychain, but doesn't require the user's passcode. For instance, email password to Microsoft Exchange. How many of you are using Microsoft Exchange in your iOS device? Yeah, a few. ActiveSync, basically. So the ActiveSync password, Wi-Fi shared secrets, and things like that. So that's one other example of an attack. Before I talk about the third example, I'd like to illustrate a picture about what a man-in-the-middle attack is, because you might have heard of it, but never seen the concepts behind it. One way of doing a man-in-the-middle attack is, from an attacker's point of view, doing an ARP cache poisoning on both the device and on the switch or the router that is controlling this network. And that basically fools both the device and the router to send network traffic via this attacker's computer instead. So, but of course, if this is SSL or TLS traffic, then still the attacker would need a trusted certificate because otherwise the user would get a warning. This is an invalid certificate, or this certificate doesn't match the server name that I'm connecting to. But the problem is, in iOS, there was a vulnerability that was fixed in 4.3.5, and where the Apple developers didn't do a correct chain of trust validation of certificates. So a normal chain of trust is that you have your server certificate at the bottom, and that in turn is signed by maybe an intermediate CA, and at the top you have a trusted CA that is trusted by the device platform. The problem was in iOS before 4.3.5 that it didn't even check on those certificates what the basic constraints, the allowed usage of those certificates are, which means you could take any approved certificate and sign that, make that sign new server certificates. And that's, of course, a big no-no in terms of PKI structure. So what does this mean for man-in-the-middle attacks? That means that I could generate an arbitrary amount of server certificates and sign those with the certificate that I've got from VeriSign, for instance. And I could do man-in-the-middle eavesdropping or affecting the network traffic sent over SSL TLS. So looking at antivirus products, I know that F-Secure, Symantec, McAfee, all those companies, they're really, really struggling to get access to as many mobile devices to read the application package of what's been installed in the rest of the system. But on Android, at least, you can read the initial installation package. But that's it, basically. So for instance, if we have malware that gets installed in the system partition, and we read-write protect that with root privileges, that means that the antivirus product wouldn't be able to detect that. And also, since the antivirus product is communicating through the public API, we could even affect the public API if we are at system level and if we have full access to the device. So think about this before you buy an antivirus product. There are good, for Android devices, there are good antivirus products like Lookout, for instance, if any one of you is using it, that can be downloaded for free. It's at least something that scans for malware and can detect those packages that's been out there for a long time, but still it has pretty limited effect on new malware. So there's still a time window before Google reacts and before Lookout reacts and understands what the malware does. So as I mentioned before, I'd like to talk a little bit about what kind of vulnerabilities that we find in our code reviews. So the iOS developers, maybe it's a bit difficult for someone who hasn't seen Objective-C, but the iOS developers should recognize this at least. Can anyone tell where the problem is? Come on. Nothing wrong with this? That's absolutely correct. The problem is that this line of code, it relies on that data buff is of the same size or smaller than temp buff, and there is no way we can guarantee that, since data buff is being sent as an input to this function. And but looking at a slightly more advanced example, this is, by the way, those are examples from real applications that we have reviewed, even though we have modified it a little bit so that we can easily present it. So looking at this example instead, anyone who can see any problems with this? So the first thing, maybe I should explain that this is actually reading data from a TCP socket, network traffic. It's using NS input stream, the read function, and the read function it has the return type int, which means it's a signed integer. It might return 0 if it's the end of the stream. It might return negative values if an error occurred. So what happens if we take a negative value and store that in an unsigned integer? It's going to be an implicit cast to unsigned int len in this case. So negative values will end up as extremely large values, which is certainly not expected in the rest of the code. So that could cause buffer overflows. It could cause that we're allocating huge amount of memory, or at least trying to allocate huge amount of memories. And if we don't do a null check after that, for instance, then even more problems can occur. The next line of code is calling a function called read length from buffer. You see the signature at the top. And that's also returning int, which means this could have the same problem too, depending on the implementation of read length from buffer. So what read length from buffer does is, after we've read the buffer or the byte data from the network stream, then read length from buffer will decode the first bytes in that stream to detect the exact length of a certain message. So looking at the implementation of that, it's pretty scary, because it might return error codes, and those are defined as negative values. There is an off by 1. Off by 1 means that in this example, it should be -2, but it's -1. And when it's decoding the length of the total length of the message, it just takes byte by byte and shifts it 8 steps. Which means if we have 4 bytes, which means 32 bits, which means a full integer, that's going to mean that we can end up with negative values too. We might even end up returning 0, which again might not be expected by the code that's calling this function. The reason we might end up with returning 0 is that even if this is an add operation, we might have a negative value. So let's say that length after this is -4 and count is 4. That's going to mean 0 as an end result. Of course, there are platform protection mechanisms for this. One example is ASLR. That's going to make it a little bit more difficult to utilize different kind of buffer overflows. But still, it is possible. By the way, even though there isn't ASLR protection in 2.3.3, this attack that I demoed is using a similar brute force kind of technique to detect where a certain function in libc are. There's also one kind of protection is to set permissions on memory regions to say that this memory region doesn't have execute permission, for instance. But that can be resolved by return-oriented programming. How many of you know what ROP is, return-oriented programming? Not as many. But so the thing with return-oriented programming is that since you can't execute since you can't just execute stack or heap memory, what you instead do is you utilize a buffer overflow to make the program counter jump to something that you know in libc, for instance. And libc memory has execute permission. And if you know the instructions there, then you can prepare registers to have certain content based on what you want the code to do. And from there, you can jump to another location in libc, and so forth. So even though stack and heap memory is not executable, it's still possible to utilize buffer overflows. To summarize a little bit the difference between iOS and Android, of course, review is better than no review. We mitigate the problems with that I, as an attacker, might try to upload an application that pretends to be the legitimate banking application. That can easily be mitigated with the App Store review. But at the same time, we have seen examples like Charlie Miller this week about that there are things that is difficult to detect or can just be something that Apple will miss in their review. One thing that we are seeing with when we work with governments is that they like Android for one reason primarily, and that it's quite transparent in terms of the security design in the platform. And that's what they don't like in iOS, that they can't really measure the security. They can only trust what Apple are saying in terms of security. But of course, at the same time, there's tons of other stuff they do like about iOS because it's a fantastic platform. And something that's really good about iOS is, of course, the rate of software updates. And in the same way, that's a problem for the Android platform. So looking at a typical security update, if a security issue is found in the software platform, what happens in both cases is that it's either Apple or Google that corrects the security issue normally. In the Android case, it could be one of the the other companies involved in the Android ecosystem. But it's about the same time, actually. One could always argue that it's a day back and forth, but I think this is about the same, at least in the issues that I've followed up. The big difference is that from that point, it's only about a user of an iOS device to actually install the update. But in the Android case, the manufacturer has to decide, well, what devices should we update? And when in time should we package this update? Should we do it this update only? Or should we have the next cool multimedia feature and wait for that next cool multimedia feature to get tested and verified and all that, and carrier improved and all that kind of stuff? So that's the biggest problem, that there's a time window, additional time window for Android devices that the iOS devices doesn't have. Of course, the companies involved in the Android ecosystem, they have understood this and they're trying to resolve this by minimizing the differences between the vanilla Android experience and what the manufacturers are adding. But still, there's a long time before we will have something that looks about the same as in the iOS case. Google publishes statistics about platform versions, and that's really interesting. That's done on it's about 2 weeks basis. So looking at the attack that I just demoed today, it's 2.3.3 and earlier that is vulnerable. So that means the red part, and I can tell a big part of the purple section. It's not as many devices that have received something later than 2.3.3, but the reason it's presented within the same amount is that it's the same API level, and this is actually statistics of API levels rather than the exact versions. So, and of course, the 1.5 to 2.1 is also still a big part, unfortunately. So the point here is that more than half, certainly more than half of the devices are vulnerable to these kind of attacks that are actually performed today. Comparing that to iOS, we don't have any official numbers from Apple. The only thing we know is that the Apple guys always say that they prioritize getting updates out as soon as possible, especially for security updates. And I'm convinced that they are doing a real good job there. But again, there is no exact numbers. There are statistics from independent companies. One company is called Chitaka, and they presented numbers early November this year that about 2/3 of the total amount of devices that they are in contact with are still using 4.x, which means a big part of this red section is vulnerable to, for instance, this SSL TLS vulnerability that I presented. And this also tells us that just because Apple has published updates, that doesn't necessarily mean that everyone downloads it and installs it on their device. And we have a customer that they have a mobile device management system, and they did measurements or reports on the version statistics of their iOS devices within their organization. And about half of the devices did have 4.3.3 and earlier. So again, it doesn't necessarily mean that everyone updates it. And that's why it's so important, especially in an enterprise organization, that you enforce certain versions to be so that it's either you update your device or you won't get access to the backend systems. You can't, of course, you can't force like physically force the user to to update their device, but you can always do it with a stick and carrot approach. Like if you do that, then you will get access to the systems again. So to summarize a little bit, stay updated. I think that's pretty clear. And in the Android case especially, choose the hardware you use carefully, especially if it's for corporate use, because there are big differences between one manufacturer towards another in terms of their rate of updates. And also be careful, independent on what kind of platform you're using, be careful what you install. Again, especially if it's a corporate device, or especially if you have it connected to your sensitive data, like corporate email through ActiveSync, for instance. And in the Android case, check the permissions that an application is requiring. But as you saw in the demo, maybe we can't trust it fully, but at least it's a starting point, and it's something to get worried about if an application is requesting internet permission and doesn't necessarily have a good motivation for having internet access. And if you develop in-house applications, and of course if you develop applications that you sell through the App Store or the Android market, it can have significant effect if you introduce security vulnerabilities in your own code. So be careful and review the code that you develop yourself to make sure that you don't have any security problems. And in an enterprise organization, it's really good to use an MDM tool to make sure you know exactly what versions and what kind of devices that you have out there throughout the organization, and also being able to control and enforce, like for instance, passcode complexity. One example being alphanumeric passcode is a good starting point. You can also use an MDM tool to distribute client certificates, or add in the iOS platform, and from Android 4.0 and forward, you can add trusted certificates. And that's all that I wanted to present. So I'd like to know if there are questions. Yes?
With Delta updates, why don't they check what you have on this?
What you have already? Yeah, so that's one thing that's important to mention. There are solutions that does that, but there is no guarantee that just because you have over-the-air update, that the over-the-air update mechanism actually checks what you have. So it's not the entire truth that Delta update wouldn't detect this. It might or might not. So if you, for instance, if the Delta update contains checksums of the existing components, then of course that's good. But normally, or with the assumption that nothing has changed the system software, especially if we have the system partition mounted as read-only, and if we also have write protection for the flash memory that system software is stored in, then maybe we might think that, well, there is no reason for checking it because we already know what's in there. Does that answer? Yeah. Yes?
Do you think these mobile antivirus models really make sense? Or they're just a huge scam, or maybe even additional risk?
I think the risk is that the users might get the impression that, well, I'm safe because I'm running an antivirus product. And that's suddenly the impression that Symantec and McAfee and all these companies are trying to give you. But the point is that they are extremely limited, much more limited than they are on PC platforms, for instance. So I would say that, I would say that it's something that's good to have as a health check, but it doesn't give you the exact truth. it doesn't even do that on the PC systems either. So it's quite small detection rate, even in the Windows platforms, for instance, since much of it is signature based and malware tends to modify itself. Does that answer you? Yeah.
Just a small comment. I can just check my phone and I have some security app from Samsung,
Mm.
and it has a huge list of permissions that is required.
Yeah.
And I think that's scary because
Yes.
that might be an attack vector by itself.
And that's a really important point. I think that's a great comment because about the permissions, it's not only about being cautious of suspicious applications. It's also about applications that might look legitimate, but if they introduce a security vulnerability within the antivirus product itself or in this Samsung security app, then of course utilizing such an attack would already give us a lot of permissions without even privilege escalation.
Could you then say that if you don't support older versions, you actually do your users a favor?
Yeah, the user might not see it that way, but I think in terms of security, you're certainly doing your users a favor if you make sure that they get their devices updated. But of course, that's also a matter of planning and designing your mobile device management solution and making sure that you actually have methods for providing those updates. And because another problem that has been a problem before we got iCloud for iOS devices is that many companies didn't allow the users to install iTunes, which made it even more difficult to update their devices. So, and that's also an interesting thing. Because many companies have policies about